Now we're going to take a look at problem 7.4. In this case, that problem deals with battery manufacturers compete on the basis of the amount of time their products last in cameras and toys. And a manufacturer is saying that their battery lasts an average of 26 hours when used in a toy racing car, and the amount of time is normally distributed with a standard deviation of 2.5 hours. So part A is, what is the probability that the battery lasts between 24 and 28 hours? So the first thing we want to do is convert that to a standard normal distribution. So part A, we've got what's the probability it lasts 24 to 28 hours. But the first thing we want to do is calculate, for instance, a z for that 24. So in this case, equals 24 minus 26, which is the average, and I should put that in parentheses. And then we're going to divide that by 2.5, which is the standard deviation. And that's going to be equal to minus 0.8. So that's for the 24. And for the 28, it's the same thing, equals 28 minus 26, which is the mean, divided by 2.5, and what we're going to see is this, that it's a positive 0.8 on the z-score. So, it's important, once you know that, to be able to put some arrows in and draw the picture, because that'll help you understand what area you're really talking about. So I'm going to drag one of these arrows down here. So 0.8 is roughly here. And I'm just going to copy this, Control C and paste, and drag it over here. And I could put in 0.8, but I think you get the idea there. So we're talking about calculating the area right here between plus 0.8 and minus 0.8 standard deviations. So I'm going to scroll over here, and you can see that calculation right here. So we've sort of done that already. That just shows it to you. And the other way to put that this would be the same as equal to, well, it would be P minus 0.80 is less than Z is less than 0.80. And so now we have the options for doing this calculation. I'm just going to pause for a second. So now that we know the z-scores, there's a couple different ways to look at this. And the first thing that I'm going to show you is how to use the tables in the back of your book. So if you go to page 310, which is Appendix B, it's got z-scores. And on the left-hand column, it goes from 0.0 down to 3.0. We're going to go to 0.8. And the value of 0.8 is 0.7881. And you'll notice, if you look at at the top there of that normal distribution, that goes from a positive 0.8 standard deviations, and it gives you the probability of everything from there to the left. And if I flip back one other page, I can see that I've got negative numbers from negative 3.0 down to negative 0.0. So if I look at negative 0.8 in that first column, 0.00, it gives me the number 0.2119. So let me put that page. .309 for minus 0.8 and 0.00. Page 310 for 0.8 and 0.00. And once I have those two numbers, I could go like, just go equal to the probability to everything minus, again, notice on the top of page 309, it's giving you the probability of everything to the left of minus 0.8. And that's what we want. If you remember back here, I'm going to go minus or equal K6 minus K7 for 5762. Again, if you look at those graphs on the top of the page, the first one for the positive 0.80 gives you everything from here over. And then from 0, -8, it gives you everything from here. So if you take this minus that, all you're left with is the probability in the middle, which is that 0.57762. So that's an effective way to do this. The other way to do this is to use the calculation of the normal distribution. So I'm going to go equal and go NOR, and in this case returns the standard normal distribution has the mean of 0 and standard deviation of 1. So I'm going to double click here, and the z-score I'm going to put in there is 0.8. Again, I've got to separate the items asked for. Z, now it's asking for cumulative, and I'm going to put true in there in this case. Close the parenthesis, and that gives me that same 7881 I see up here. And I'll do the calculation for the other right here. Equals normal, and again the normal S distribution, in this case minus 0.8 and the cumulative is going to be true in this case. And again, you can see that I match that. If I went over here and shrunk the number down to the same number of decimal places, you see it matches exactly. I can do the same thing here. And now if I go equals this minus that, the 5763, I mean it's close, there's a little bit of rounding error in there, but basically you've got the same numbers here and here. So that would be another way to do that calculation. Now, for part B, we want to know, I'm going to take this away. We want to know what the probability of the battery lasting longer than, is it 28 hours? Yes, and so we know that the 28, that value is the 0.8. So in this case, what we want to do is, we know that this 0.7881 was the probability covering everything from here over to here. So if we want to know what the probability is here, we know that the total probability under the curve is equal to 1. And if we subtract the probability of everything from here over, that is going to give us the probability of it being greater than 28 hours, the 2119. Now, in addition, I'm going to pull this away and bring this one back up. With this z of minus 0.8, when we looked that up in the z-table on page 309, we knew that this area less than here was equal to 0.2119. Well, in this case, the 24, which we calculated up here, remember? It was the 24 minus the 26. The 26 was the average and the 2.5 was the standard deviation. So we know that here, that calculation is simply the value of P for Z less than minus 0.80, which we already know is this value right here. So it's equal to 0.2119. So the same probability, because they're both 28 is 2 greater than 26, 24 is 2 less. Since we've normalized it, it would be the same probability, it being greater than 28 or less than 24. So I hope that's helpful. Again, the normal distribution is an extremely important part of continuous probability distributions.